I want to introduce three equations we'll be using in our problem solving called the kinematic equations, and you've seen some of it before. Here is a velocity versus time graph for an object at time 0 has initial velocity vi, and at time t has velocity v. If we use the first data point and the last data point to calculate slope, we know the slope is the acceleration, which is the change in velocity over the change in time. Using y equals mx plus b for this straight line and making the appropriate substitutions, we get the velocity at any time t is equal to the time multiplied by the acceleration of the object plus its starting velocity. This is the first kinematic equation. For the next kinematic equation, we're going to start with this idea that the displacement of an object is equal to its average velocity times the time that it's moving. We discovered this in our first unit of constant velocity motion, but it always applies. As long as we use the average velocity of the object, even if it's changing its velocity, multiply by the time it's moving, we will know how far the object went. I'm going to use this previous equation down here and solve that for t and substitute it in this equation. If I do the algebra to rearrange this equation and solve for t, I get time equals velocity minus initial velocity divided by acceleration. You can look above to see where that came from. Now I'm going to substitute this time in there, and that leaves me with this. And now I want to write another expression for average velocity. And average velocity is always the velocity something has plus its initial velocity divided by 2, as long as it's increasing its velocity at a uniform rate. So now the original expression is the product of these two quantities. And if you carry out the multiplication here, this results in the velocity squared minus initial velocity squared, all divided by 2a. And now let's simplify this more. Alright, so we start out with delta x displacement, and we know that it equals this, so here is what we have, and this simplifies too. And I can go one more step and write it this way. This is the second kinematic equation we will use. The last equation comes from the idea that the area beneath a VT graph is equal to the displacement, or the change in position. So with that idea, displacement is the area. I can write it this way. This first term here is this shape right there, the triangle, and this is the area of the rectangular shape. By the definition of acceleration as the change in velocity over time, this expression is true for this case here, which means v minus vi, if I multiply both sides by t, equals at. So I will substitute a times t in for that right there. And I have that written here, and this can be simplified further as displacement equals 1/2 a times t times delta t. T and delta t are the same. So we'll write that a t squared plus initial velocity times time. So this is a third kinematic equation that we will use. So in the past we used graphs to do problem solving, and we can still use the graphs, but these equations come from the previous work we did with graphs. This is simply the equation of a velocity versus time graph we'll be using. This was derived from a basic idea about average velocity and displacement. And this one here is just an equation form of taking the area under a velocity time graph for an object that is accelerating. So instead of having to draw the graphs, we can go right to using any one of these three equations or any other one in the past that we've used.